Okay, now we're going to move on to a subject called heat exchangers. Now it's really important that you go into the web pages, the YouTube things that I've put in the accompanying material, which is an AUT Online. There's some quite nice animations, there's some nice pictures, there's a bunch of things there which I think will really help to illustrate this. But basically, let's just start off with looking at a very simple heat exchanger. I won't go into that just for a second. Let's imagine that you've got some hot water flowing along on a pipe. I'm going to draw the pipe with this particular shape and you'll see why. Okay, so this is hot. And I want to cool it down. So if I put this into a bucket of water, then obviously the water is going to be cooled, the hot water here is going to be cooled down by conduction into the cold water, and it's going to come out cooler. We don't know how much cooler, but it's going to come out cooler. So that's one simple way you could make a heat exchanger. A better way might be to get your two pipes, and we'll get a pipe. And we can join those two pipes together. Now these little diagrams that I've done over here are essentially like this. So it's sort of like I've got a pipe coming in and it's going down, and I've welded another pipe to it over here. So the fluid comes in that, comes down that pipe, comes out there, and the other one might come in here and go up that side and come out there. So that's a bit like what I got there. Or they could be two boxes touching each other. There's a number of designs that we can do. I'd like you to look in the material that I've put online. You can see that there is three very common types of heat exchangers. There's the shell and tube, there's the plate, and there's a cross-flow type. Okay, so now let's go back to this and have a little look at how these heat exchangers can work. Let's imagine that we've got actually a kind of heat exchanger that you've all seen. You know, when you do a distillation, you have this kind of thing coming out of the distillation. Ooh, I drew that really badly, didn't I? And there's your thermometer. Here's your Bunsen. This is called a Liebig condenser. And this is what we call a shell and tube condenser. This is the shell, and the bit going up the middle is the tube. And you remember that cold water comes in here and comes out there, and your hot vapors come down here and condense. Absolutely standard type of shell and tube condenser. So our diagrams here could possibly represent something like that, where perhaps you had your hot material coming there and your cold material coming on the outside of that. So let's go over to here and let's just sketch this up again. This might be your shell, that might be the tube. It doesn't really matter a lot. Now there's two ways that you can put the flows going through. One of them is where you can have them going in the same direction. We call this co-current. Or we could reverse the directions and we could have it going like that. And we would call that countercurrent. Now in fact most heat exchangers are run in a countercurrent way, and I would explain why. Most biological systems where you're transferring heat, let's say your body is trying to warm your fingers, then hot blood's coming in and cold blood's coming out, and the heat is being exchanged on them. Animals like huskies that can happily run in the high Arctic at minus 30 degrees warm the pads of their feet in a very, very efficient countercurrent process. the chemicals in your body. You have, for instance, fresh oxygen-filled blood coming from your lungs and blood coming back from where it's been. They also go in a countercurrent way so they can get the maximum gas exchange. Okay, so let's come back here again. So we've got two ways. Let's have a look here at the co-current. So what I'm going to do is I'm just going to actually twist that diagram sideways. So it looks like this. Okay, so we're going to have one flow coming in there and the other flow coming in there. We'll call that hot in and cold in. And this one here would be cold out. And this one would be hot out. Now let's draw a graph. So come down here then, we're going to have a graph of temperature versus distance. And temperature. So here's hot. So we're going to say that's hot there, whatever that temperature is. And as it goes along, this one here is going to get colder. It's going to be cooled down by the cold. And here we've got the cold coming in. And that's going to be warmed up. The thing is that because you can only make heat flow from a hot body to a cold body, as soon as the temperature here drops down to the same as the temperature here, you're not going to get any changes in temperature. So if I continue this on further, say, they would eventually merge together. Or if this was a very efficient heat exchanger, they'd sort of merge before they got to the end. So this is a co-current. Nothing wrong with it, but depending on what you're trying to do, normally the countercurrent is the way to go. So I'm going to now draw a countercurrent, same sort of thing, but what I'm going to do here is I'm going to draw a very slightly different graph. So here we've got hot in, hot out. It's no longer probably hot, actually. I'm saying hot out because it's just that flow. It could be quite cold by now. And how we're going to have a cold in and a cold out. So let's just say this is point A and this is point B. This is where the two pipes are joined together. So let's draw our graph again. So this is A and this is B. So here's our hot coming in, and it's going to go down and it's going to get cooler. This is our hot out. Now our cold is going to be coming in, and let's say this is how cold our cold is. Our cold is flowing this way, so it's going from B to A. So that's going to be warmed up. And it's going to come out at that temperature there. So I'll put a little arrow on it just to indicate the direction of flow. I see on here I've got A, B, C and D. Well, maybe we can relabel this. So B, C, A and D like that. So that's where A comes in, all the way down to B. Twisted this, remember? Not doing it all well there. That would have to be B, wouldn't it? And you guys work with me. If C comes in here, this is then going to be D out there. Right, so that's D there. Okay. Now these numbers are the same as this, but remember I've just turned this sideways because I think it actually corresponds better to the diagrams. I should change that in my notes. So let's go back and have a look at these. Let's compare them for a second. So these are the flows. If I had A and B, this is A, and that's A, and this is point B there. So they come together. In this case here, they come, one goes down and one goes up. Now, unlike this one, if you look at this, it's quite possible to have the cold flow warmed up a lot hotter than the hot flow comes out at. And likewise, the hot flow can be cooled down a lot more than the cold comes out at. So as a result, it's possible to get much more extreme heating and cooling. If you've got a very efficient heat transfer, the heat's going through, it's possible to get the cold out almost to the same temperature as the hot in, and the hot out almost as cold as the cold in. Ultimately, they can't be exactly the same because you can't move heat from a hotter body to a colder body, to a colder body to a hotter body. Dear me. You know what I mean. Hot goes to cold. So those are your two kinds of heat exchangers, your co-current and your counter-current, or the two ways of running the heat exchanger. Now there is a third way, and this third way here is for a cross flow. Now where do we find cross flows? Again, have a look at the online material, but let's say you've got a car. I'm going to draw a very simple kind of car, sort of a bit like a Jeep. Now at the front here you've got a radiator, and you've got cold air coming in, and the idea of the radiator is that the heat from the engine comes in at the top, is cooled, and goes out at the bottom. So if I looked at that on the side, here's my heat exchanger, my radiator. It's my engine, and the hot in and hot out. Now there's no cold flow, no liquid cold flow, but for the car we've got air, and it's going crossways, not in the same direction but sideways. Here's another little diagram that I drew which is a little bit closer to it. So we've got a series of pipes, and the air, or it could be a liquid, it doesn't have to be air, is going sideways, and in that case we get a slightly different graph. As you go, the air going sideways is going to be warmed up, and the liquid going at 90 degrees is going to be cooled down. So you get curves that look something like that. So I've already mentioned these types of heat exchangers. We have three fundamental types, although you probably only generally run across two: the shell and tube and the plate. So in very simple terms, a shell and tube is just like a Liebig condenser. Shell, tube, and the liquid coming in, and we would normally have countercurrent and the liquid going around it this way. Now if you want to make a bigger, more efficient one, you have a lot more tubes and a lot more shells, and I really recommend that you just look that up. The online material is really good. There's animations, there's really nice pictures. And the same thing is true for the plate heat exchangers. The plate heat exchangers are very much like the kind of diagram that I drew here, where we have liquid flowing over a plate. So this is, if you can imagine, it's a bit like this. We've got one little box, and we've joined that up to another little box, and then between them is this very, very thin plate. So the liquid comes in and goes out, and the other liquid goes in, the box on the other side, and comes out, and that big thin piece of metal in between them is where the heat goes through. Very thin, so it's very easy for the heat to get through. If you just join a bunch of these up, and do look at the pictures, it's much, much clearer in the pictures, you get a flow pattern which looks something like this, and you get a design which looks like this. You can have a few plates, you can have lots of plates. Plate heat exchangers are very popular in places like the dairy industry, partly because they're very efficient, and partly because you just have them all squeezed together with nuts and bolts, Then when you want to clean it, you just loosen all these nuts and bolts and pop it open, and you can hose it down and clean your heat exchanger. Shell and tube designs are normally designed where you want high pressures, high temperatures. They can be made of steel, they can be made of glass, they can be made of stainless steel, all kinds of things, but they're a bit harder to clean. So you have a whole lot of tubes inside a big box, and it's just like a big version of that one there. So here's some advantages of the shell and tube types and the plate types. I'll let you read that. You'll find plate types are very popular in the dairy industry, as I mentioned. Shell and tube, you tend to find them in most other applications, largely because of simplicity. And the last thing I want to talk about is energy recovery. We're not going to say a tremendous amount about energy recovery, but in modern systems, energy is expensive. Doesn't matter what kind of plant you've got, energy is expensive. So if you can use heat exchangers to save you energy, then it's a very positive thing. Here's an example. Let's say you're trying to boil water. You can start off with cold water at say 15 degrees and boil it, no problem. And you can use it to do something like cooking food or whatever it happens to be. And then you can just get rid of the steam when you're finished. Or what you can do, one example would be you can pump out the used hot vapor, the used steam, and you can run it through a heat exchanger and extract heat from it. So that goes away as just now a cooled down, probably warm water, and the cold water comes in and gets heated up by the steam coming out, the used steam coming out. And instead of going into the boiler at 15, it might go into the boiler at 80 or 90, so it doesn't require a lot of energy to heat it up. So this is the process of energy recovery, and there's a whole range of things that can be done. That's one very simple example. You can use energy recovery in many, many places where you have waste energy of some sort. So you'll find in modern industries that's very, very commonly done.